In this video, we're going to take another look at how we find N in electrochemical and redox processes. This comes up on your mud cards fairly frequently, so I thought it would be a good time to make a video about it. Now, a key feature of any redox or electrochemical process is how many electrons are transferred in total. This value is N in many equations we use, such as the three you see below. Now, how to find N? There are a couple ways. You can find it out from half reactions. This is going to be the least common multiple for the electrons in and out. This least common multiple is N. You can also find it from a balanced equation. You want to assign oxidation numbers, count how much the oxidation loses, and the reduction gains. So those two numbers will be equal because the electrons are transferred, and these numbers are equal to N. Let's take a look at how redox and oxidation processes happen first.
Let's look at a redox process in terms of the half reactions. So this is going to be the oxidation first. I am currently Dr. S0. I have my electron. But what's going to happen is I'm going to get oxidized. Goodbye, electron. I am now Dr. S plus 1 plus an electron. Let's look at the reduction half reaction.
I'm Dr. Amoroso. I'm currently in the plus 1 oxidation state. I can become reduced by accepting an electron that happens to be floating in space. I'm reduced. Now I'm Dr. Amoroso in the 0 oxidation state. Let's take a look at what this looks like when two oxidation and reduction species are actually interacting.
Now you're going to see both of us interacting with each other. So I'm again starting as Dr. Sterner 0.
I'm Dr. Amoroso plus 1.
I'm going to lose my electron and get oxidized. But now instead of the electron floating off into space, it's going to get transferred right to Dr. Amoroso. So now that electron that went out in the oxidation and in the reduction is outright transferred from Dr. S to Dr. A, and the reverse can also happen. So that's why we don't add the electrons in and out. They're the same electrons. They're just getting moved from one species to another.
Finally, let's wrap up with a few examples. Our first example, we're going to have aluminum and phosphorus becoming aluminum 3-phosphide. The oxidation reaction that's happening here is aluminum becoming aluminum 3 plus 3 electrons. The reduction is the phosphorus gaining those 3 electrons to become phosphorus 3 minus. Our electrons in and out match, therefore our N equals 3. Here's another example. We're going to have tin 2 plus 2 electrons becoming solid tin paired with gold becoming gold plus E minus. Our electrons in and out don't match, so we need to find that least common multiple. In this case, it's 2. All we need to do is multiply this gold oxidation by 2 to get it to balance. So now we have 2Au becoming 2Au plus 2E minus. 2 electrons out, 2 electrons in, N equals 2. Let's try some that are a little more complex. Now we have manganese becoming manganese 3 plus 3 electrons, paired up with Br2 plus 2E minus becoming 2 Br minus. The least common multiple of 3 and 2 is 6. We have to multiply our oxidation by 2 to get to 6, and we need to multiply the reduction by 3 to get to 6. Our new equations are 2Mn becoming 2Mn3 plus 6 electrons, paired up with 3Br2 plus 6 electrons becoming 6 Br minus. 6 electrons in, 6 electrons out, N equals 6. One more. This is the equation for iron becoming iron oxide in the presence of oxygen. When we balance it chemically, we get 4Fe plus 3O2 becoming 2Fe2O3. What we need to do is understand what are the separate oxidation and reduction half reactions that are happening, and then the stoichiometry in this overall equation will tell us what we have to multiply each of those processes by to make the electrons balance. Well, first off, our iron is going from iron 0 to iron 3+, and we can tell that because oxide ions are always -2 charge. Therefore, that O3 makes for a total of -6 charge that's balanced out by 2 iron cations. So each one of those must be 3+. So we have our process Fe becoming Fe3+ plus 3E-. We're going to multiply this whole half reaction by 4 because we have 4 iron atoms and 4 iron ions in this process. Looking at the oxygen, the relevant half reaction here is O2 plus 4 electrons becomes 2 O2-. We're gaining 4 units of negative charge, so we have to add 4 electrons in total. We're going to multiply this half reaction by 3 because we have 3 molecules of O2 in our reactants, and we have 6 oxide ions total in our products. Now, if we translate that multiplication through, what's happening is these 4 iron atoms are transferring a total of 12 electrons to the 3 oxygen molecules, converting everything to iron oxide. This means that our N equals 12. I hope this cleared up a few things for you. I am happy to see you in class.